So remember we talked about the difference between a transverse wave and a longitudinal wave, where a transverse waves, the medium moves up and down, up and down. And in a longitudinal wave, the medium moves back and forth. So here I draw a representation of a transverse wave. That would be like, a wave on a rope that you're wiggling back and forth, or waves on the surface of a lake or on the ocean. And a longitudinal wave, uh, longitudinal wave is where the medium moves back and forth. A longitudinal wave, an example of that is a pressure wave or a sound wave. A sound wave is a longitudinal wave. Instead of the medium moving up and down, the medium is moving back and forth. And this causes big and small pressure waves or pressures in the medium. So in this cartoon diagram I have, this would be a big pressure, and then this would be a low pressure. The regions of high pressure we'll call condensations. The regions of low pressure are called rarefactions. I will show you a spring in class, and it'll look like this, and you can establish a compressional wave where I have the spring is all compressed, and then it's stretched out, and then it's compressed, and then it's stretched out, and then it's compressed, and then it's stretched out. These would be the condensations here, and the rarefactions would be here. But when we're talking about sound, that's going to be an area of high or low pressure within the medium, which is the air or whatever the sound is moving through. This feature of pressure waves is an application of the ideal gas law. So if you recall, in the ideal gas law, PV was equal to N times R. Oh, excuse me, sorry I did this wrong. Your book actually, I think, uses PV is equal to NKT. But we've seen before that PV is equal to nRT. These are both constants, so effectively for us, these are the same equation. This gives us the number of molecules or atoms, and this gives us the number of moles, but it's still a measure of the amount of the gas. All right, so what we're looking at here is the amount of the gas. If the amount of the gas goes up, it increases, that means that the pressure will also increase. That is to say that P is proportional to the amount of the gas, that the pressure is proportional to the amount of the gas. Again, let me just make this clear. It comes up on the next page, where N is the number of molecules, a capital N, in that first rendering of the ideal gas law, but lowercase n is the number of moles. So both of them are representing the amount of the gas. Oops. Sorry about that. The number of molecules in a particular region increases. Molecules are atoms, the number of particles. So the pressure increases. A direct proportionality between N and P. Sound can also travel through solids and liquids. While it's still a longitudinal wave, we don't call it a pressure wave, because it doesn't really change the pressure of the medium. It doesn't change the pressure of the medium. It's not in an appreciable way, because, solids and liquids are both incompressible. We saw that in a previous chapter. So if they're incompressible, then you can't have condensations and rarefactions. But the waves nonetheless travel through those materials. In fact, we'll see later that they travel much faster through liquids and solids.